So we're continuing our lesson on solving systems of equations and inequalities with graphing. And so this part B of lesson 1.2 is now we're solving systems with graphing of inequalities. So we're going to combine the ideas of how to graph inequalities that you learned in lesson 1.1 and graphing our systems of equations in the first part of 1.2 and put them together to graph these inequalities. Now, when you were solving graphing inequalities before, we only had one equation. So let's first review that with just one problem here. On example E there, sorry, I should have examples A, B, and C, but they're labeled E, F, and G. On example E, our first inequality statement is x is greater than 2. If this was an equation, it would be like saying x is equal to 2. Well, how would you graph x is equal to 2? There's no y in the equation, so how are you supposed to get it into y equals mx plus b form? The answer is you don't. When you have no y term in the equation or inequality, then that is a vertical line. And whatever it's set equal to, or the inequality is pointing at, that is the point on where you'll be drawing that vertical line. It should not have a y-intercept then. So find that too on the x-intercept, right there, and draw your vertical line going up and down. Just like so. So there's no y-intercept, so there's not a slope to look for in the equation. So remember, vertical lines have no slope, so it's just a straight vertical line. Hopefully you start to recognize these by now. Just incidentally, what if the equation had a y is greater than or less than or equal to some number? That would be an equation or an inequality of a horizontal line. Okay? So because this is an inequality, we need to then ask ourselves, well, is it dashed or is it solid? There's no equal to sign underneath the inequality symbol, so this should be a dashed line. So you can go back and erase. If you don't like going back and erasing, or what I definitely recommend when you're drawing these on paper, is that you first draw your pencil line very lightly and then go back to erase and then go back and darken up your dashes so that you can clearly see that it is a dashed line. Now I am actually going to wait to shade, but I am going to do something different here. I did show you this once before in the first part, or in lesson 1.1. I use these things, I call them shading guide arrows. They're just on either end of the actual line that I just graphed that points in the direction that I would like to shade towards. Let me go ahead and do that, but do not color in the full shading yet, and I'll show you why. So this inequality says it's greater than 2. Well, greater than means it's pointing to the right. So on either end of my inequality symbol, I'm just going to kind of draw some tiny little arrows pointing in that direction, saying if this was the only line that I was trying to graph and I was ready to shade, I would shade everything to the right of this line. I'm going to wait to do so though, because I actually have two inequality statements that I need to graph on the coordinate plane, and the shaded section needs to be where there would be an overlap. I'll explain here in just a second. Let's go ahead and graph the second line. So my second inequality statement, y is greater than negative 2x plus 3. I'd look for that y-intercept again. So there's a negative 3 y-intercept right there. And I'd use my slope, negative 2 over 1. To go down 2 because it's negative, and always run to the right 1. Always run right unless you have to back up because you fell off the graph. Clean that up a little bit. My one dot got there we go, or point. I keep on saying dot. Sorry. If I ever say dot, you know that I'm referring to the actual word. It's called a point. So I need to connect my points with a line now. And just like before, then I need to ask myself, is this line supposed to be solid or dashed? There's no equal to sign underneath my inequality symbol, so this is also a dashed line. And just like before, I need to add some guide arrows to show in which direction would I normally shade. Well, this is a greater than sign, which means that I would shade everything that was above this line, or as you go up on your y-axis. Alright, so before I go into explaining what is the only area that you would shade, which by the way, what I would say is look at your guide arrows, find a guide arrow from each one of the lines and that are pointing towards one another. The guide arrows that are pointing towards one another are this one and this one here. Let me explain why that is, or here, let me back this up just for a second. You do not need to copy down what I'm showing you right now, I just want to use it to explain. So in lesson 1 we learned, if we're looking only at the blue line, we learned that if it was greater than, then we would shade everything to the right of that line. So I'm just going to shade that in that light blue. And if we were looking at that purple line, it would be everything that's above that line. Do you see that? Everything that's above just the purple line would be that section there. But because we have both of these lines on the same coordinate plane, what we need to know then is, well, where do those two overlap at? They overlap in this section right here on the coordinate plane. Where the blue and the purple overlap is the only area where any point that falls in that section would solve both the first and the second inequality at the same time. Okay, so when you graph these, we only care about where they would overlap. This is where those guide arrows come into play. So you wouldn't normally have two colored pencils to graph these, which does help and make it easier to graph to make sure you know which line you're talking about. So instead, and on the ECA, they will just show you the two lines together, one dash, one solid, both the same color, and only small section shaded, just where they have overlapped is the only thing you would shade. So again, this is where those little guide arrows that I explained will come into play and be helpful for you. So you shade where the two guide arrows are pointing towards one another. So just this section right here. You can go ahead and shade in now just that section on your paper. When you're done, push play and then, or push pause and push play when you're done, and we'll look at the next examples. We'll do it together again. Okay, I'm ready to graph and solve example F here. So I need to graph, oops, I had the wrong tool there. Alright, sorry. Okay, so first I need to graph the first inequality, but there's a problem here. Do you notice it? It is not in slope-intercept form, so you need to rearrange that inequality to get it in slope-intercept form, which is what? You should have this down by now and memorized. Y is equal to mx plus b. Alright, so if we want it y equals mx plus b, our y term is where it's supposed to be. That 4, or positive 4, is not where it's supposed to be. We need to move that to the other side of the inequality. We still use the same inequality symbol, the less than or equal to sign. The x stays put, but that 4 is what we're trying to move to the other side of our x. So that should be a negative 4, because when you move that term to the other side, it becomes negative. Sorry, I tried to finish that sentence while yawning. Alright, we're doing that because you're moving a constant from one side of the inequality to the other. You'll do that by subtracting it from both sides. That leaves it negative 4 on the opposite side. So a good rule to remember is when you cross the inequality or the equation, you change the sign. When you cross the line, you change the sign. You probably heard that in Algebra 1A. Alright, so you're ready to graph that inequality statement. You find your negative 4 on your y-intercept. There it is. Using the slope, find the next point on the graph. Your slope is positive 1 or 1 over 1, so you go up 1 over 1. Always run to the right. Connect the 2 points with a straight line. Whoops, wrong tool. Connect the 2 points with a straight line. Now we need to ask ourselves, is it dashed or is it solid? There's an equal to sign underneath your inequality symbol, so that means it stays solid. So that equal to sign only lets you know whether or not to make it dashed or a solid line. Has nothing to do at all with shading. Now we need to do our guide arrows to show in which direction you would shade if it was the only one that you were graphing. So it's less than. That means as we go down on our y-axis. So use your little guide arrows to point down on either end of the inequality symbol. You don't necessarily need the one in the middle, but that helps to explain. This is as we go down on our y-axis. Try that again, sorry. There we go, there we go. There's your guide arrows. Alright, we're ready to now graph the second inequality. So we can do this in purple so you can clearly see it. Once again, our inequality is not in slope-intercept form, so let's convert it. We're going to have to do this in 2 steps. I think there might be enough room to solve the problem right here. Let me see if I can, sorry, if I need to zoom in. I'm going to have to work it a little bit on the graph. Sorry for interfering there. I leave my y term where it's at. Yes, I know there's a 2 in front of it, but I'll have to do that in the second step. Greater than. I have to move that 4 to the other side of the equation, so that's why I did not copy down that positive 4. Negative 3x. It stays where it is because it's then your x term, and now we're ready for the constant. That constant needs to move to the other side of the inequality, so we're at a minus 4 because I have to change the sign. Now I still need to get y all by itself. Now's the time where you divide by 2. Every term divide by 2 because it's beside our y. The 2's cancel out, and you get y is greater than. Our inequality does not change directions. Remember, what causes our inequality to change directions? If and only if the number you're dividing by is negative. So if that y term had been negative, then yes, our inequality would have had to have changed directions. But that's not the case here. I just want to remind you of that rule, though. Okay, negative 3 halves x. And then a negative 4 over a positive 2 equals a negative 2. Ready to graph this? We look for our y-intercept of negative 2. That's right here. Use that slope to find the next point on the graph. So we have to go down 3, 1, 2, 3 because it's negative, and run right 2. You always run to the right unless you're falling off the graph. Connect your points, the straight line. Ask yourself, dashed or solid? Because there's no equal to sign there. This is a dashed one, so you need to go back and turn it into a dashed line. I'm just going to erase. And then guide arrows. Oops. The inequality says that it's greater than, so that means as you go up on your y-axis from that purple line there, or above the line. And then our final step is to shade. Shade where you have a guide arrow from each line, one from each, that are pointing towards each other. This line is pointing to this line. Therefore, this is the only section that you would shade on the coordinate plane. You can finish copying this down. Push pause until you finish copying it, and then push play when you're ready to go on to the last example problem. In example G, our two inequality statements are currently in standard form because our x and y term are on one side and then our constants on the other side of the inequality symbol. Had these been equations, my preference would not to convert this to slope-intercept form. I think, remember, there is another way to graph equations, and that's using the x and y intercepts. But because these are inequalities, inequalities can be tricky. I can use my x and y intercepts to graph them this time, but when I say they get a little tricky is if your y term is negative and they're in standard form, remember that your inequality symbol will switch its direction, which means you could get your shading messed up. So I would still convert these to slope-intercept form, even though they are standard with no coefficients. And that's how it. Okay, so let me stop for a second and explain to you real quick, or remind you how to graph using intercepts. In that first inequality, it was x plus y is greater than -4. If you were just going to graph this using the intercepts, it's ideal when your coefficients are 1, like in this situation here. Because your intercepts, if you remember, your x-intercept is when y is equal to 0. Well, if y equals 0, we can cross off that y term, and what's x equal to? It's already by itself, -4. So that's your x-intercept. Your y-intercept is just the opposite, when x is equal to 0. Well, if x is equal to 0, the y's would still be there. Then that means that y is equal to -4. If you were to plot those 2 points, those would be the 2 points of your intercepts. So this right here, these are the intercepts for this first equation right here. And you can plot those. -4, 0 is right back here. And the other intercept is 0, -4. That's down 1, 2, 3, 4. It's right there. So you can connect those points together, form a straight line. Using the intercepts. Now you need to follow this, all the same steps after this with, okay, is it solid or is it dashed? Because it doesn't have the equal to sign, we do need to make this a dashed line. And then we need to make our guide arrows. Oops. So when it's in, if you're going to graph just using intercepts in standard form, you must make sure that the sign of your y term is positive. If it's negative, then that inequality needs to change directions. Alright, it's positive, so that means I make my guide arrows in the same direction as the inequality. It says greater than, so I make my guide arrows point up. If that's too confusing, it's okay. You can still use slope-intercept form. That's the form that we use the most often, and it works in every scenario. So if you're going to only stick to one method of graphing, at least learn how to graph from slope-intercept form. Now on the ECA, they will ask you questions like what is the x and y intercepts. The x-intercept you can only solve by replacing all the y's with 0. Okay, so that was a lesson from Algebra 1A. Alright, I'm ready to graph the second equation. This time I'm going to go ahead and continue using the slope-intercept form that you're maybe more used to. Sorry, I'm yawning tonight. So I leave my y where it's at, less than or equal to. I need to move my x term over to the other side, but because I changed sides of the inequality, I have to change its sign, and then plus 2. I did not change signs on that 2, so that's why it stays positive. Now that I've got it in slope-intercept form, I need to plot the y-intercept at positive 2. That's right there. Oop, got that one a little big. There's that point. And then using the slope, which you see the negative sign in front of x, that represents a negative 1 then over 1. So I go down 1 over 1, always run to the right. And then I connect my, whoops, wrong size arrow, just a second. Then I connect my points with a straight line. We're going to notice something different about this one. But it's something we should have probably predicted if we had kind of compared our inequality statements before we started graphing. Alright, so there's my solid line. Should it be, there's my line. Should it stay solid or do I need to dash it? It has the equal to sign, so it stays solid. Now I need to make the guide arrows for shading on it as well. And notice that it says less than or equal to, so less than means below the line. This is kind of interesting. And now we want to know where would we shade. The solution would be only where we have our shaded section. So they both, all the arrows are pointing towards each other. So the only solutions to these two statements are right here and here. What do you notice about those two lines? You see how they're parallel? Had these been equations and not inequalities, there would have been no solution because they're parallel lines. But because they're inequalities, there's that shaded region that you have a possible solutions for as well. So we have a shading above one line, below the other. It's only in between those two lines. We could have recognized that we were going to have parallel lines because we noticed that our coefficients of y are exactly the same, and so are our x's, but our constants are different. So whenever you have two equations or inequalities whose coefficients of your x and y term are the same, but your constants are different, then you're going to have parallel lines. Except for, well, that's going to be another lesson coming up. In lesson 1.4 later on, you're going to see parallel and what are called coincident lines. Alright, so those are your three examples. You have an independent study practice to do after this. Again, there's only a few problems, but we're going to continue giving you practice on this quite frequently. So that's the end of this lesson.